from my end in the on laptop. All right. So we have posted homework 5, and you should be able to access it. Problem 1 you can solve after today, and problem 2 you will be able to solve after Wednesday. But we'll kind of make sure that they're slightly more involved than the lectures, but they are not too bad. Okay. So we have posted homework 5, and we'll have office hours usually, like usual, and then I'll mention more about the homework 5 on the next lecture. All right. So a quick recap. We have been talking about boundary layer theory. So we last time discussed boundary layer theory. And we had discussed how there are different regions in a boundary layer. The outside region is called the inviscid region, where basically you can use del square phi equal to 0. This is mu is equal to exactly equal to 0, and tau is equal to 0. And we will basically use the potential flow to solve this problem. Okay. So this was the idea outside the boundary layer. Just to clarify, this is this region outside the boundary layer. Okay. All of this region. So this is what you did in your part 2 of the course, is do this outside problem. And then inside, we basically defined this boundary layer region. Boundary layer region, where we derived the velocity, we said there is some delta boundary layer thickness. And we showed that last time, delta by L is same as Reynolds number to the power of half, inverse of the Reynolds number to the power of half, which is equal to 1 by rho u L by mu, the power of half. Okay, so this is, if you recall last time, we discussed this, and we said basically that lambda by L is much more than 1. And that's why we could derive the boundary layer equations, rho del Vx by del x plus Vy del Vx by del y is equal to nu del square Vx by del y square. Sorry, I missed another term. U du by dx plus nu del square Vx by del y square. Okay, so this was our equation. Any questions about any of these regions and how to solve them? Any, like, in terms of like how to get to this point? Oh, good. The first part, you solve the outside problem. And remember, from the outside problem, Vx of x comma 0 leads to this u. Okay, so I just want to really emphasize this, that this leads to this u. And you can definitely solve the problem. Okay. So this is what we will discuss today. Basically, last time we discussed how to get the scaling analysis of lambda is much smaller than 1, and how to get to this boundary layer equation. Recall that we had discussed last time that how this equation is non-linear. We have Vx times Vx in the equation. We have also discussed that Vy, which is this part here, is actually already coming into the system. And the outside region also influences the boundary layer. So this problem is obviously much more complicated than what we have seen before. And so don't forget that we also have the continuity equation that you have to solve together, because you have the Vy, which will now be connected through the continuity equation. Okay. So is this clear? Any questions until this point about to set up any problem that you see of this nature? Okay. All right, so you have this, and we have started this problem through a floor on a cylinder. And in your homeworks, you did like a floor on a sphere. When you just solve the outside problem, you got drag 0, which is the DL paradox. Technically, now basically what we want to do is we want to solve the inside problem. So if you solve the inside problem, technically you should be able to get to the drag. The challenge here is that this problem of cylinder turns out to be more complicated than what we have shown here. So we'll start with even a simpler system, and then I will discuss briefly towards the end of the lecture what happens in this more complicated problem. Okay. So to do that, so let's try to simplify the system further. Simplify the geometry further. Simplify the geometry further. And basically we'll focus on a flat plate. A flat plate. Okay, so that's the idea. So you will not focus on a cylinder because cylinder, as you can imagine, has a more complex geometry. And I'll discuss what happens. I'll discuss about that in the later part of the lecture. But let's just start with a slightly simpler problem where you have a flat plate. Okay, so imagine that you have something like this. Velocity is u naught, flat plate, and some sort of a boundary layer here. And just in case it's not clear, remember that the boundary layer is how you go towards velocity, right? So the goal is find drag on a flat plate. The idea is simple, that first we want to solve the flat plate before moving on to cylinder. We have seen in cylinder, if you don't solve boundary layer equation, you get drag to be zero. So that's why we want to solve the boundary layer equations. But solving the boundary layer equations in a cylindrical problem is much more difficult. So that's why we're taking a step back and saying you solve a flat plate problem. Okay, is that clear? So again, don't forget there is outer region where we have del square phi is equal to 0. And again, ignore gravity for simplicity. Del square phi is equal to 0, p by rho plus v square by 2 plus h is equal to 0. And then we have the inner region, which has del vx by del x plus del vy by del y is equal to 0. Vx del vx by del x plus vy del vx by del y equal to u du by dx plus nu del square vx by del y square. This is the system. This is what you want to solve now for a flat plate. And then you will calculate, and eventually you want to calculate drag. So in the outer region, you have a flat plate where you're basically flowing some velocity u naught on top. Yes. Oh, so this is constant. Thanks. What was the other question? Oh, thanks. This is habit on both sides. Yeah. So there is no gravity, like Felipe mentioned. So gravity is 0, right? And so it's simply thanks, Felipe. Okay. That's good. All right. So now outer problem. I hope you can see in outer problem there is no geometry change, right? There is no geometry change. It's just like imagine this is the surface. It's just something is flowing on top, right? And there is no viscosity, right? So I hope you can all agree, and you can satisfy this. You can all agree that simply this will mean that Vx is u naught and Vy is 0, and P is some constant. It's some constant. It could be 0. You can simply solve this, and you can see that this will satisfy your equations and the boundary conditions too, because it is just constant everywhere. We know, like on the left hand side. So this is a trivial solution, and that's why we did this, because as you can imagine, when we solved the potential flow problem around the cylinder, we had a velocity profile, right? So that's what this problem is trying to do, is trying to simplify our life by saying, well, in the outer region, I will get a trivial solution. Okay, so this is a trivial solution which satisfies everything. And don't worry, like even if it's not obvious, this is just something it's designed in a way to get this solution. So trivial solution. Okay, you just get this. So what does this tell me about my inner problem? Does it help me somewhat in my inner problem or no? Anybody wants to take a guess? Pressure gradient will be 0. Yeah, that's a good point. But what in terms of the equations I have here? The boundary conditions. Yes, Colin?
Well, you have two terms, right? Like you don't have the ux, dx, and you don't have the dy. So,
all right. So good point. So first thing is that note that, so what Colin was saying. So I think sorry you mentioned that pressure is constant, and we discussed that, well, pressure really outside is what is the pressure inside, which is a good point. But we don't have the pressure written over there, which is embedded in the u du by dx term. So I'll come to that. So that's a good point. The other comment was about the boundary condition. It is true that the boundary condition is simple. The boundary condition is simply u naught, right? When you go further away, it is simply u naught. There is no equation as x, but we'll come to that again. The whole point here is that we have both vx and vy, but actually we cannot say that vy will be 0 inside. It can be a boundary condition, but it cannot be something you can say inside. But this u du by dx term, right? This u du by dx term comes from outside. This comes from here, right? So this comes from this vx of x comma 0 is u, right? And in this case, because it's u naught, everywhere it's u naught, right? So this, it's just a constant. So it's u naught du naught by dx, but u naught is constant. So that means that I can drop this term off. Okay, so you can think of it in terms of how Sauradeep mentioned that pressure is constant, and that term is really pressure gradient. So pressure, if pressure is constant, pressure gradient is 0. Or mathematically, you can see that velocity is u naught, velocity is u naught, and it's du by dx. Does it make sense? Okay, all right. So we get this equation, del vx by del x plus del vy by del y equal to 0. And we get vx plus vy del vx by del y is equal to nu del square vx by del square. So we have these two equations, and we need the boundary conditions. So now, what should be the boundary conditions and how many? Any thoughts? Anybody wants to suggest boundary condition? Good. So I believe Sauradeep mentioned y equal to infinity. So vx x comma infinity. You approach u naught. So this was the matching condition, right? Where you approach the velocity far away. I need know that there are two derivatives in y with respect to x. So we need another one in y, and that is the no slip. That is simply the no slip. And this no slip condition was what was causing all the pain, right? If you could just do it in the outer solution, you wouldn't be doing all this. So this is very important that you have the no slip condition, and then you also have the no penetration condition. So these are your boundary conditions that you need to solve while solving these equations. So again, I want to emphasize how we got here. Potential flow does not give us drag. We derived the boundary layer equation last time. Now we are saying we focus on a flat plate because it drops off this u du by dx term. And you simply get this equation, and now we have these two equations and boundary conditions. That is why that is how the process goes. Okay. So before I actually help kind of solve this problem, I want to first also focus on some order of magnitude analysis estimation. Okay, I really want to focus on that because, in my view, if you can do the order of magnitude analysis, you can do the problem. Okay, so it's really important to understand and appreciate all the different scales of this problem. So there are some differences. Please note, don't get confused. I want to make sure this is very clear. Is that now we will be doing order of magnitude analysis on a general X. And to not confuse you, I will write this as delta X of X. So I will write this as some sort of a delta X of X. Okay. So this is just to mention this is a position dependent boundary layer thickness. Okay. Delta X. And again, obviously, we have this X here, this Y here. The full length is L. Okay. Full length is L. All right. So now I want to do the boundary layer analysis. Okay. So I want to, order of magnitude analysis, OM analysis. OM analysis. All right. And so the difference here is, and I will let you do this in a bit, but I just want to mention this. You'll all agree that Vx is U naught, right? Does this make sense to everyone? This Vx is U naught for each X. So, right, for every X, this is roughly true, right? Then delta X, remember I had done this initially as L, but now I am saying it as X, okay? So I want to clarify this, is important. So just don't forget this. Delta Y is delta of X. So I am basically now trying to make it a bit more specific rather than finding some general delta. I want to find as delta of X. Then finally, I think that's all you really need actually. So I want you to now take a few minutes and I will walk around. So take a few minutes to do OM analysis on both continuity and boundary layer equation. On both continuity. Sorry, I think the so both continuity and boundary layer equation. So please take a few minutes, do that, and then I will discuss how to do that. So what I want you to find eventually at the end is what is the formula for delta X. Delta X. Okay, what is the formula? Okay. Take a few minutes. Yes. So that's a great question. So it is similar to the delta at when X is equal to L, but we want to find for a general X, and that is important because when we solve the equation, we will basically employ this order of magnitude analysis. So it is related. It's not different. It's just that it's saying rather than finding for a length L, we are finding the boundary layer thickness as it's kind of going along different X values. Yes. Oh, why? Because you already have the continuity equation. So if you apply order of magnitude on both of them, you will get the answer. Okay. So please try. Yeah, any other question? How is the X different from delta? They both depend on X. The other one we had, if you remember, we had defined only on the length head. So what you're asking is a great question if they are both very related. So sort of like we are repeating analysis here a little bit, but just the fact that it means that you will replace L by X everywhere. And I just want to emphasize that don't get confused because there are two lengths here, one is X and one is length. So yeah, but you can simply just use the last one as well. So they are very related. They're not completely different. Okay. So take a couple of minutes. I just want you to repeat this analysis. And the order of magnitude analysis is very important. So that's why please take this time, try to do this on your own, and then we'll discuss. All right, so maybe let's see how we can do this. Hopefully this is becoming very, second nature to kind of see order of magnitude analysis. So we will do the quantity equation. It's u naught by x because it's vx by x, and then vy by delta because vy we don't know and delta x is the scale of y, and vy becomes u naught delta x by x. That makes sense. And then when we go to the boundary layer equation, it's Vx del Vx by del x. So Vx and Vx in numerator is V naught square. Denominator is delta x, so it's x. Then we have Vy del U by del Vx by del y, Vy by delta times U. And note Vy by delta is same as U naught by x. So they're both similar to U naught square by x. We'll drop the 2 sign because we don't carry the p factor. And then the right hand side is mu, U naught by delta x square. Because it's mu del square Vx by del y square. And so you rearrange and you get mu x by u x u naught. Okay. So first things first. First note that it increases with x, which kind of makes sense that boundary thickness is increasing as I'm going along the x dimension. It's increasing at square root of x, which is very interesting information. As you will see in your course later down, there are other boundary layer thicknesses which goes as 1/3 or 1/4, and here we are going as 1/2. Okay, so square root of x, and this is momentum boundary layer. So it's an interesting kind of factor. The momentum boundary layer thickness increases in square root of x. Then it decreases with an increase in velocity, which also makes sense that if I'm really flowing fast over the flat plate, I'll have a thinner boundary. Okay, so it's kind of intuitively correct. Okay, any questions here? Okay. All right, the next question to all of you is on the order of magnitude analysis is how will you estimate the drag force? So you have this, we don't want to solve it right now. How will you estimate the drag force? What do you think I should do to calculate the drag force by the fluid on the plate? How to estimate drag force? And we are not calculating this. I'm just saying how to do an order of magnitude analysis. Any thoughts? Great. Does everybody see why? So what Tim is saying is first, I hope all of you can see this, that because of the geometry, so maybe let me just sketch this plate like this. We're flowing something on the plate, right? I am not talking about the drag force, is not talking about the perpendicular force, right? So there are two parts, pressure and shear stress, right? And then you can calculate a stress vector and you can calculate both the forces. But because the geometry is such, and you can do the full calculation, it's not required. It's obvious that if I'm sliding something on the surface, and I'm just shearing the surface, I'm not applying sort of like a normal force. Okay, that is not true for other geometries, and that's why we have moved away from cylinder for now. In cylinder, you can imagine we can also be kind of like using pressure force to kind of apply a drag, but here we're just applying a surface drag, and that's called skin drag. Okay, because it's parallel, it's only because of the shear, and we'll discuss skin drag in a minute. But for now, the point is what's interesting to us is to estimate the tau. And what we will want to estimate is a tau normal to x, so normal to y, and parallel to x, and that is equal to, and this is sometimes simplified further because this is equal to, mu del v x by del y plus del v y by del x. I hope you can see that this term can be ignored because this is vy by x, whereas this is u naught by delta x. And we know that u naught is much bigger than, it is clear that we can kind of relate them and this number will come out to be small, or simply tau yx, which is sometimes referred to as wall stress, is tau wall is equal to mu make sense? Yeah, so what I'm saying is, maybe let me just clarify. So what I'm saying is del v x by del y scales as u naught by delta x, whereas del vy by del x scales as vy by x, which is equal to u naught delta x by x, right? So I'm just taking the continuity equation And then this will become U naught, kind of similar to how you did in your other problems earlier in the course. So it will become delta square by x square. So this is very small compared to the other term. So this is because it has a factor of delta by x whole square, so very small. Make sense? Does that help? So now I have this. So first thing is to calculate drag, we need the stress vector. We said we'll ignore the pressure because pressure is not going to apply the drag, it's normal force in this case. And then we have the tau yx, which is the mu related to the y equal to 0. And if I want to scale this, how will I scale this? I will say, what do you think is our delta y? This pen is. Does this make sense to everyone? Del v x for del y would be u naught by delta of x, right? Does this make sense? Anybody has questions here? It's very important. Okay. So you have this, and now I know what my delta x is. I know my delta x is this, so substitute that mu u naught by square root of mu x by u naught, and what you will get is a fascinating result that says this is equal to mu u naught cube rho by x. Okay, so please try this and confirm that, and you remember that nu is mu by rho. So I've kind of used that mu by rho. Please confirm and convince yourself that this is what you get. Mu u naught cube rho by x, all in square roots. Any questions? Sorry? Because there is a mu here, so it has a mu also in the denominator. So that cancels out with the mu, one of the mu, right? Does that make sense? Yeah. Does that make sense? So where is the shear stress maximum? At the start of the plate or at the end of the plate? Start, right? The x is equal to 0. The x is small and it's very high initially. And as you're increasing the boundary thickness, the shear stress is going down. Now, how is the stress varying? Stress is varying with square root of mu. Isn't that strange? Like you had always heard that stress is proportional to mu. No, the shear stress is proportional to square root of mu. Why is that happening? I mean, physically you would expect it to be mu, right? So why do you think physically it's square root of mu and not mu? Thoughts? Ideas? So whenever we used to think about previously, before this topic of boundary layer, we had a fixed length scale, like a height or a radius. Now the length scale itself is the boundary layer thickness. And the boundary layer thickness is a function of mu. So it's very interesting, and this is a very insightful result. It looks very simple, but this is very insightful. Note that you are in a high Reynolds number regime, but your viscosity matters first, right? Viscosity matters in a high Reynolds number regime. But it doesn't matter as much as the kind of usual regime where it's proportional to mu. It is square root of mu. So it's important, but not as important. Okay, so that's the first part. And why is it happening? It is happening because your length scale, this delta, you never had something that was changing. It was always height or some sort of a length of the channel or a radius. But now it's dependent on this itself is dependent on the flow and the properties of the fluid. A length is dependent on the flows and properties of the fluid, which is why you kind of get to see this interesting behavior. Okay. Another part, which is again, this simple result is fascinating here, is that it is u naught cube, right? It's u naught cube square root. So it's u naught to the power of 3 by 2. And do you think it's good or do you think it's bad? like what, so what I'm trying to, so let's take one step further. So the drag force, and I'll discuss this. Drag force note is for the full plate. This is not local anymore. This was a local result dependent on X for full plate. So there I will say, I will find it as tau W at a length scale of L times the area. And area should be the parallel area, right? So area should be the parallel area, which is length times here. And I'll define a W here, which is like this. So this is mu U naught cube rho by L times WL. So you get U naught cube rho L times W. This is your drag force. Okay, so this is the drag force. You can confirm this. This is the parallel area. Area parallel. Okay. And finally, we'll also define something known as the drag coefficient. Drag coefficient, which is FD, and we'll define this as rho U square by 2 times area parallel. In this case, we are defining it like this. And I will let you do this. I apologize. I have to kind of do this a little faster, but you will get this out to be rho U naught L by mu, or 1 by Reynolds number to the power of half. So you can verify this. This is just the ratio of drag force to some sort of inertial scale or kinetic energy times the area parallel is the way I have defined a drag force. Or I have defined the drag coefficient. Okay, and that's what we get. So I want to kind of really take some few seconds here to explain why this is such an important kind of observation here. Is that in a very high Reynolds number flow. So what is Reynolds number? It's the ratio of inertial stress to viscous stress, right? That is Reynolds number. And what is that? So let's go back. Okay, so Reynolds number is rho U L by mu, and you can think of it as rho U square by mu U by L. Okay, this is what you can think of. Think of Reynolds number as that. So it's the inertial stress to the viscous stress. High Reynolds number, you would expect, so high Reynolds number, you would expect that inertial stress dominates, rho U square dominates, right? That's what you will expect. And if that is the case, you would expect that the drag force to be proportional to U square, because your stress which is dominating is proportional to U square. If my viscous stress was dominating, then I should expect it to be proportional to U, right? So is everybody following this? So this is very important. I mean, you can forget everything about this, but you have to understand this physically once. Okay, that look at those two terms, rho U square and mu U by L. If it's just inertia, it should be U square. If it's just viscous, it should be U. So in your drag force on a sphere on a particle, you had 6 pi mu U, right? Mu U. There was one U linear with velocity U. But here we are getting at as U naught raised to the power of 3 by 2. Right? This drag force we're getting here as U naught raised to the power of 3 by 2 in a very high Reynolds number regime. And that's the beauty of this whole result, is that it's saying it is not as bad as a U square. That if you're doubling the velocity, my drag force will not be 4 times. It will be 2 raised to the power of 3 by 2. So it's not as bad, as long as I can make a boundary layer like this, right? As long as I can make a boundary layer like this. And this principle that doesn't hold U square is behind all design automobiles, all design of aeroplanes, all designs of wind turbines, is to reduce the drag force. And that's why they have the shape they have. So we'll discuss this. Yes, Paul.
It seems interesting to me that we're defining the Reynolds number like parallel to the flow, like parallel to the flow instead of like transverse perpendicular. Like,
you mean the length L, or what is
yeah, it's just I feel like most of the time when we do Reynolds numbers, it's like
yeah. So excellent question. So what Colin is saying is why am I using the length scale L? Why am I not using some length scale? That's a great question. It's a very insightful and deep question. So The reason it's defined like this is literally because there is no other fixed length scale in the system. We literally just have the length of the plate. But you may have a channel. Let's say if you have a channel, in which case you can choose to define it in terms of height. So it's always Reynolds number. There is always this question of length you choose. But note that that is still independent of the velocity discussion. It will still be u naught square, u naught. So length part is absolutely correct. But we are not kind of focusing on that right now. We're focusing more on the velocities. So there might be a length ratio that will come out if you define it differently, but the velocity dependence will still be the same, right? Okay, so does that make sense? So this whole result of scaling analysis is very crucial for that. Okay, so I just really want to emphasize, like, I have taught this course and I feel like if you can understand this scaling analysis is not that important here. It's important to understand the scaling analysis. Really appreciate all the details here. Is that okay? How does this, and this is how I remember this topic. I forget the math many times, but this is the physical understanding of this is really crucial. Understanding and appreciating how, if I have the drag like this, it's somewhere between inertia and viscous, because you have a boundary there, which is connecting the viscous and the inertia. It's kind of like, it's amazingly beautiful result. Okay, so we'll discuss this now, how to do the full math. I'll skip over some of the details, but I'll discuss how to do this and how Blasius derived the result. And then we'll end with discussing more about the sort of physical interpretation. Okay, so let me set up the problem before taking the break. So let's set up the problem. So we have done this. Now we have this. I'll just copy paste this here. I'll take this. Let's come back to this here and then try to solve this problem. Okay. So we have this here. These are our governing equations. Okay. And our boundary conditions are Vx at x comma infinity is u naught. Vx at x comma 0 is 0 and Vy at x comma 0 is 0. Okay. So this is what we want to solve. So what's the first challenge? What do you think is the first challenge in this problem? Nonlinearity. So sorry, this is nonlinearity. So what have we learned till now? We don't want to solve problems in multiple variables. We don't want to solve nonlinear problems, and we don't want to solve PDEs, because PDEs are more difficult to solve. So the first step is, as you can see here, the first step is that we can clearly see that there are two variables, Vy and Vx. So we want to eliminate Vy, right? So how did we eliminate Vy previously? Similar, but the stream function, right? That we said that because there are two equations, I don't want to use two equations. I just want to write one equation. So first, I mean, it's kind of, I'm just trying to show you the thought process on how one solves it mathematically. You have the equation, okay, stream function helps me get rid of the variable. I'll then only have psi, because automatically the condition will be satisfied. So Vx is del psi by del y and Vy is minus del psi by del x. I might be changing the sign here. I might be splitting between these and it's just out of convenience. It doesn't matter, but as soon as we put this equation automatically gets satisfied. That's the first point, right? Because del square psi by del x del y minus del square psi by del x del y. So then I only get one equation, which is this one. Vx, so this, I will just write it down for you. So it's del psi by del y, del square y, del x del y. So I'm just substituting this here. Then I have minus del psi del x, del square psi by del y square to new del cube psi by del y cube. Okay, this is the first point, that we get del psi by del y, del square psi by del x del y minus del psi del x. This is Vx, del square psi by del y. So in case this is a bit unclear, this is basically, I'm just substituting all these terms here. Okay. And boundary condition, what will be the boundary condition? It will be Vx is del psi by del y Okay, so these are a boundary condition. This is now one variable equation which has three boundary condition, which we should technically be able to solve. So first complexity going from two variables to one variable, changing the boundary conditions as we go along. Now, what's the next complexity? PDE, right? We have both depends on x and y, PDE. So what you really want to do is to convert this into an ODE. Okay. So what's your hint here from your previous, whatever we have discussed? What is your hint here to use which method and why? Okay, why? Why do you think we should use similarity? Right, semi-infinite. So semi-infinite domain. You see, right? We have discussed this. Whenever you see a semi-infinite domain, the obvious thing to think about is similarity. So let's take a 5-minute break. Once we come back, I'll introduce the similarity. I will skip a bunch of steps just because I feel like it's a cumbersome derivation. I'll tell you how to do it, and I encourage you to do it yourself. But I will kind of just give you from the final results, and then we'll discuss more on the physical interpretation of this graph. Okay. So let's come back at 12:57, 5 minutes from now, and then we'll carry on with the discussion.
Yeah.
Yeah, no, so I've had this one half this one.
Yeah.
It's more generation amount I will announce it. Yesterday I quoted the Blasius. Oh, I see. Because
Yeah, that was the first time I saw it.
got it. Hi, Sophie.
Yeah, I had a question last night, but I completely forgot to ask you after. It was in the experimental moment with the I did it to give us time to do it ourselves, so I really expanded like every term, and I ended up maybe it was the one you mentioned. Okay, when I expanded, I kind of had the first term cancel out, like the opposite of what we saw, and so I was wondering what are the
Right.
which ones do we cancel out?
Yeah, so it is both both dimensions. So in the experiment, we get there square. Student y square, the y that's the edge. You did it correct?
Oh, okay. Right. I'll record this, so you remember what I did, and then we. Okay.
Correct.
Okay.
Always. You like now.
All right, let's get started. So we'll continue our discussion on using similarity. So just recall that we are discussing this problem of boundary layer of a flat plate, and we want to think about similarity transform to solve it, and we want to find similarity solution for psi. But how do I even start? Like for a similarity variable, you need some sort of similarity in the solution. So what do you think this process is similar? I mean, so as an idea, semi-infinite, yeah, great, semi-infinite use similarity. But for us to propose a similarity solution, I would think about something that should be self-similar, right? So we thought concentration was self-similar or concentration difference was self-similar. What do you think should be self-similar in this problem? Boundary layer, right? So so the idea is, well, the velocity profile is sort of increasing in sort of the boundary thickness, but what if I divide by the boundary thickness and normalize by the boundary thickness? Would that yield a self-similar solution? So the idea is that Vx, we are proposing that Vx is some sort of u of f by f of eta, where eta is our similarity variable, and remember eta is similar to y by delta. And we have done delta of x, by the way, because we are thinking of scaling every time from the usual sort of the local thickness. So this is equal to y by nu x by u. Okay, so the point is Vx should be u times f of eta, where eta is equal to y by, this is a proposition. This is not that has happened. This is a proposition. Okay. That's the first proposition, u times f of eta. Okay. But I'm not solving for Vx. I'm solving for psi. So how do I go from Vx to psi? Yeah. How do I go from Vx to psi is, we know the definition. We know how to scale Vx now, but how should I scale psi is written in the formula. So we know that Vx scales as del psi by del y. And so the psi should scale as Vx times delta y. Note that this is delta y scales as del x. And so essentially our proposition is psi should be nu x by u times u times f of eta, which is nu x u times f of eta. This is our proposition. This is very important. I will spend again, give you a few minutes to digest this, but this is extremely important to understand how we have come to this place. Okay. So the first idea was to say, well, similarity should be between the boundary layer. Boundary layer is growing, right? So always remember how we thought about this. We said, well, we'll basically compress the y-axis or the x-axis in a way that it starts to look similar. In this case, clearly the velocity profile is developing over a longer and longer boundary layer. So we're normalizing the y dimension by the boundary layer thickness so that it goes somewhat between 0 to 1. So that's the first idea. But we said, well, that doesn't work because I'm solving in psi, not solving in Vx. So we said, oh, but we also know the formula for psi. So that means that psi should scale something like Vx times delta of x. Now Vx was as u times f of theta, right? That's from this proposition. And delta x is similar to mu x by u. So that's how. And then you just plug in and you get this as a proposition. Okay. Yes, please. Oh, sorry. Thank you. Yeah, this is actually everywhere it's u naught. Thanks, Sophie. Thanks a lot. This is u naught everywhere. My mistake. Yes, thank you. It should be u naught everywhere. Please, if I wrote u anywhere here recently, please make sure it's u naught so that you don't get confused. Anything else here is clear? Okay. Yes, please. No.
That's supposed to be going to u naught.
So which one?
Right above.
Yeah, it's Vx times L.
But yeah, it's u naught.
Vx. So good question. So note that this one here. So that's the full scale. Absolutely right. That means my f of theta should be between 0 to 1, but we're trying to go towards similarity. Now we're not trying to just simply say, so maybe it will be a little clear if I write it like this, that this is absolutely u naught, but this f of eta is added to get an exact solution. So if I was just doing an order of magnitude analysis, I can say psi is root mu of u naught. That will be fine. But we're not trying to find a similarity solution. So add the functional form on top of it. Does it make sense? So you're right. So you're thinking around the right direction. You're saying how am I kind of sort of switching from order of magnitude analysis to similarity? I'm saying order of magnitude analysis will give you the function form right, but you need to add a factor, a quantitative factor next to it, get to the right answer. Right? And so f of theta is that quantitative factor. So yes, so Vx will be u naught, but we have added this f of theta to kind of be more quantitative. So that's the idea. All right, so we get this. So I will let you do this yourself. I will just give you the solution so that I would say you should definitely try it, but it takes some time. So that's why I don't want to spend too much time in doing this. So I'll give you the results. So del psi by del y is u times f prime of eta. Del square psi by del y square is u f double prime eta root of mu x by u. Del cube psi by del y cube is u f triple prime of eta. And by the way, I was just doing this yesterday while preparing the lecture, so this is not overly simplified. There might be some extra just to like, I'm not simplified this further. Del square psi by del x del y is half of, minus eta times u times f double prime of eta by 2x. And finally, del psi by del x. Please verify this, by the way. This may not be all accurate. So please do verify this. And I hope all of you are familiar with this. F prime means df by d eta. F double prime is del square f by del eta square and so on. Okay. Yes, please. Yeah, sorry, my mistake. It's all u naught. Thank you. Yeah, it's all u naught. I apologize. Just forgot to correct. Yes, it's all u naught everywhere. Yes. Okay. Right, so you can do the similarity and you can get to all of these different terms and then plug it back into the main equation. And what you find at the end is the equation 2 prime 2f triple prime eta plus f of eta is equal to 0. Okay, so this is finally what you get out in your governing equation. So substitute this in governing equation. Okay. So this just to show you, just once again, I'll come back to this page. This is the governing equation I'm talking about. Okay, so the top right, in the black box, that's all the derivative I calculated in terms of f of eta, substituted them, and got back this. Look at this equation. Okay, so this is the idea. Now remember that my boundary conditions were del psi by del y at y equal to 0 was 0, del psi by del y going to infinity was u naught, and del psi by del x del psi by del x was also 0. Okay. So, okay, so this is what you can substitute in, sorry, it's not the easiest to sometimes do this. Yeah, so this is what you have. Now, what do you think? So I'll just push it a little bit up here. Hopefully this you can see all of them. Looking at this left-hand side, I want to now write boundary conditions in terms of eta, right? Because that's my final variable, f and eta. So how will I go? So you see del psi by del y. What is del psi by del y? U naught f prime, right? So on top, if you see on the top, it's u naught f prime. So if del psi by del y is 0, what should be my f prime? 0, right? So f prime of 0, and you note eta is equal to y by nu x by u. So when y is 0, eta is 0, right? So when y is 0, eta is 0. So this becomes f prime of 0 is equal to 0. Now del psi by del y as y goes to infinity is what? U naught. So that means f prime becomes 1, right? So top. So when del psi by del y goes to u naught, f prime of infinity becomes 1. And this is always an interesting one that I find students to be sometimes confused by is how would you get to this one? So when del psi by del x is 0, del psi by del x at y equal to 0, 0, how should I get the value? F eta minus eta times f prime of eta is 0. But when eta is 0, the second term goes away, so simply f of 0 is 0. So what I'm saying is when this is equal to 0, when this is equal to 0, then at eta equal to 0, then the second term is already 0 because eta is 0 at that point, right? So then f of 0 is equal to 0. F of 0 is equal to 0. Okay. Any questions at this point here? Anything that's confusing? Yes, Sophie. Yeah, sure. Yeah.
When scale,
Psi, yeah, yeah. Oh, so yeah, good question. So this is basically when we were going from 2 variables to 1 variable, we didn't want to use the continuity equation. Otherwise, you have to solve both equations together, right? So we said we'll convert the variables such that the continuity equation is automatically satisfied, and then convert the second equation, which is the boundary layer equation, into psi. So that's where we used it.
okay.
Oh, I was just trying to recall what the. Yeah, we didn't use it again. Yeah, that was just there, and then we just used it to scale the variable. Yeah, we didn't redefine it or anything. Okay, so you get this. And this is basically known as the Blasius kind of differential equation we derive for this. And the main goal at the end, remember that main goal at the end is to find mu del Vx by del y at y equal to 0. And note that del Vx by del y is mu del square psi by del y square. Because note that Vx is del psi by del y because Vx is del psi by del y. So it will become del square psi by del y square. And as you can see from here, this is essentially what I'm kind of talking about. This will give you tau wall will give you square root of mu u naught cube rho by x times f double prime of 0. Okay. So I've just used, note that this del square psi by del y square. No, there are a lot of equations here. Del square psi by del y square is simply the one that I've copied pasted from the top. Okay. The equation u naught f prime double prime eta. And so this equation, just so that it's clear, this equation is what I've copied here. Okay, and then I've rearranged it to get to that point. Okay. Okay. Clear? So that's how I've gotten to that result. First things first, does this look familiar? So this was the same scaling analysis we derived, right? This is exactly the same result we derived the scaling analysis, u naught q mu rho by x. The only correction is this f double prime 0. So to Noah's point, which was that how are you switching from scaling analysis to this, is that with scaling analysis you get this, but you don't get this value. You don't get the f double prime 0, and that's why the whole analysis is done. Okay. Any questions at this point? Proportionality constant. Absolutely. Absolutely. So it's the correction to your kind of scaling analysis in a way, numerical correction. So I wasn't sure, but was this, did you solve this differential equation in your math methods in one of your homework? Okay, so you already know basically numerically you can solve this, but I'll just quickly show you if in case you did not do this, is basically this is a small code I literally wrote yesterday. What you see here is, you know, I've calculated the derivatives, I've calculated f prime double eta, f triple prime double prime, boundary conditions 1, 2, and the final one. And you don't have to worry about this, is just to show you that when you calculate this and you let it this run, essentially what you get is, and I use the nonlinear solver to get this, but the f double prime 0 I get out is 0.3319, and the one that books report is 0.332. So it was just numerically I did this, and to show you also the to the figure, this is how the velocity profile looks like. This is with respect to, so it should not be x, it should be eta. This is eta. So if eta equal to 0, we know the velocity is going to 0. When eta is going to infinity, we know the velocity should be going to 1, right? That's how it should go. So you can plot profiles, you can plot Vy and so on. So this is what, you know, you can do. So because we get that, essentially this number here is 0.332. Okay. So our tau wall, according to Blasius, is 0.332 mu u naught cube rho by x. And then the drag force would be 0 to x. I'm being a little bit faster here. This is not something, it's not too difficult. You can very well verify these things. We'll get out to be tau w dx. It will be 0.664 mu u naught cube rho L times W. And then the drag coefficient is FD rho u square by 2 A parallel is FD rho u square by 2 W times L. And if you do that, it comes out to be 1.332 mu u naught rho by L, rho u naught L by mu. Do try this. I mean, this is just a couple of steps of math, and you will do this in your homework anyways. This will be 1.332 Reynolds number to the power of -half. So essentially, we have found the prefactors for all of them. Okay, so we have found the prefactors for 0.664 for the drag coefficient, sorry, drag force, and CD of the drag coefficient. So just to remind you, this is drag force, and this is drag coefficient. Right? Yes.
That area parallel on the numerator
it's in the numerator of the fraction, the denominator. It's in the numerator of the denominator. Anything else, sir?
Special physical reason for like the 332 that sort of empirical.
It's just the value you get from math. I can't. Maybe there are some other explanations. I don't know of any myself, but this is something that comes out of the full math. Okay, so I think I might have mentioned this 1.328, I think. Apologize, this is 1.328. Okay. So these are the Blasius result, which I mentioned to you last time. Blasius was one of the first students of Prandtl who derived this, and this was very crucial in kind of thinking about, you know, drag force and so on. Okay, so this is known as the skin drag. Okay, so this is known as the skin drag. Skin drag. I want to now go towards skin drag because it is parallel to the surface. I just want to briefly discuss one more point before we close out the lecture is if we have a flow over a cylinder, which we have not discussed, your total drag force is made of form drag plus skin drag. Okay. And this is very, very important. Again, physically understanding this is probably the most important thing here is that this form drag is like rho u square by 2 times A perpendicular, whereas skin drag is mu u by delta times A parallel. Okay. So what have I done here? I'm saying there's a form drag, which is because of pressure. Okay. And this is because of shear. Okay. So there are true contributions to your drag. Pressure one we completely ignored because we did not consider geometry. We just went to a flat surface. But there will be two contributions. One will be pressure, one will be skin, and this is your kind of, you know, ratio. But now if you do FD skin by FD form, what you get out is A parallel by A perpendicular times delta by L. Sorry, I think it should be L by delta. So please do try this. I believe it's not too difficult to show this. This is what you get. This is 1 by Reynolds number. This is Reynolds number to the power minus half. Just make sure. Sorry, this is actually delta L by delta. Delta A parallel by A perpendicular. This is what you get the result. And I want to spend some time. Don't worry, you can, it will just take you a few minutes. You will be able to do this. Don't worry about sort of some of the results or the details, but it's very important to understand the meaning of this result. Okay. So it's saying skin drag and form drag. There are two contributions to each drag. Which one would you like? Would you prefer the skin drag or would you prefer the form drag, and why? Should we optimize the skin drag? Should we optimize for the form drag? What do you think I should try to optimize for and why? So if you're trying to do fast form drag, does everybody see what Jason just said? That it goes as u square. And I had done all that initial discussion that the second one goes as u naught raised to power 3 by 2. So if I'm trying to do something fast, like a windmill or like designing an automobile, I want skin drag, I don't want form drag. Ideally, you will not want to have either. But if I have to choose, I would want to choose the skin drag, right? And when I take the ratio of FD skin by FD form, I get this out. So it's saying is that when you have Reynolds number higher and higher, form drag tends to, because if this ratio for higher Reynolds number, this ratio becomes low. That means form drag is taking over. So as an engineer, what can we do? We can optimize the other ratio, which is A parallel by A perpendicular. And that's why you have streamline shapes like stream bodies, where you have, you try to maximize the skin contact by designing things like, you know, shapes like this, so that, you know, flow can have more of the contact with the skin. And that's why your A parallel by A perpendicular, you want to keep it at small values. Okay. So this is the whole idea behind this streamline bodies. It's not some, it is intuitive, but this is the whole reason. You have the drag, but you choose the one which is smaller velocities. And obviously birds and, you know, nature has also evolved in a way to minimize this drag. And it's all from this mu u by delta. It's like this u naught cube, u naught 3 u naught to the power 3 by 2, somewhere between a laminar or sort of like a viscous stress and an inertial stress, somewhere in the middle. And you want to have that, and you do that by maximizing the value. So that's why you get the stream. Okay. Any questions on this? All right. So we'll end the lecture here. Just one quick announcement at the end. We have graded your exam, and this is a distribution. So average was 48.5, standard was 9, and we'll post the results just after the class ends. Please feel free to send us a regrade request, and I will announce again on Wednesday, and we'll post the solutions as well. All right. And so I look forward to meeting all of you on Wednesday again. And I have office hours in case anybody wants to chat about the lecture. All right.